So can I start? Yes. So
Yes.
so it's a big pleasure to introduce Professor Jorge Garcés from Universidad Politécnica de Madrid to this seminar. And I think probably most of you know that Jordi grew up in Granada. He got his PhD here in Granada. So as most of the team from Granada, we are more or less exposed to non-associative algebras, and especially to Jordan algebras, G-star algebras, and some other non-associative structures in analysis. But now Jordi, after spending a few years in Brazil, he's now in Madrid working as a professor, as a researcher, and he is going to speak about some recent achievements in which invariants and Jordan structures are very deeply connected. So Jordi, you can share your screen whenever you wish.
Okay, so thank you, Antonio, for your nice introduction. Thank you to the organizers for inviting me to deliver this talk and to all the attendants. So we're going to see some recent results from preservers of truncation of triple products. This is partially supported by some national and international institutions. Here are the details, and this is a joint work with Leili, Antonio Peralta, and Shanshan Su. So let me first say a few words about linear preservers. Of course, we are going to do something nonlinear, but as many of you know, linear preservers try to characterize some linear transformations between algebras or matrices that leave function subsets or some relations invariant. Some, for us, we can think that we are working with matrix algebras maybe, or bonded operators on a Hilbert space in this first part, if you want. And here are some examples, some classical examples of linear preservers. For instance, linear preservers that preserve a certain function, such as the determinant on matrix algebras. This is one of the first examples here. I'm not going to say what are the characterizations of every one of these examples. I'm just going to list some examples. Spectrum preservers on Banach algebras, for instance, this has been also very studied. Surjective linear isometries, for instance, between operator algebras. This is also some very important type of preserver. Linear maps that preserve spectral radius, for instance. Of course, if we are in an infinite dimensional setting, continuity needs to be a sum most of the times. We have also preservers of certain special subsets in the algebra, so maybe preservers of invertibility, of idempotence, or potent preservers. Okay, so again, in an infinite dimensional setting, some continuity is needed, and preservers of certain relation between the elements of the algebra, such as the well-known zero product preservers, or orthogonality preservers, or Jordan zero product preservers. Okay, these are all very classical examples, and they have been studied broadly. Of course, there are also some preservers that can be studied in Banach spaces that are not algebras, such as healthy spaces maybe. But we are going to be interested in preservers that are not necessarily linear. When I say no linear, it's not necessarily linear. So if we want to generalize some of these classical problems, linear preservers problems, we can maybe try to, if we needed continuity, we can maybe try to drop continuity and see if we can obtain automatic continuity. or maybe we can drop linearity. Yeah, so in this case, we could study two local maps, but we are going to study this second option that is preserving single operation. What does it mean? We will see what this means. But the thing is, since we are dropping continuity or linearity, maybe we have to pay some price. So many times this means that we have to assume that our mapping is bijective and that preserves wherever it preserves in both directions, and maybe something else. I'm going to give some examples, but first I need to define what a sister algebra is. So a sister algebra is a complex star algebra. It is a Banach space whose norm is continuous and satisfies the Gartan axiom. Sorry. For instance, the algebra of bounded operators on a complex Hilbert space is a sister algebra. A volume algebra is a special type of sister algebra. It's a sister algebra that is a dual of some Banach space, called the predual. For instance, B of H is a volume algebra. And the second dual of every sister algebra also is a volume. So we have some results on nonlinear preservers, some classical results already. So for instance, we have this result by Takeda that says that if we have a bijective map, not necessarily linear map between von Neumann algebra and a sister algebra, where the von Neumann algebra needs some extra hypothesis, and this map is symmetric and multiplicative, then it is a real linear star isomorphism. So there is some automatic linearity can be achieved. This result is also true when we switch the product by the Jordan product. So it's also true, and so the result is the result by Hackett and Saito. So we have seen that some multiplicative bijections between operator algebras, that is going to be our setting, are automatically really linear. So maybe we can try to do this for some preservers instead of multiplicative mappings. So the idea is we are going to replace multiplicativity by being a preserver on products. That's the idea. Some examples of this can be found in the literature. This is already classical result by Lajos Molnar, where he proves that the bijective mapping between B of H spaces that preserves the spectrum of products of operators is an algebra automorphism or the negative of an algebra automorphism. And this is true also for the Jordan product, for instance. Some other examples, for instance, there is some notion called the delta Aluche transform that is defined here. We don't need to get into too many details, but there is, for instance, this result by Chababi that says that if we have a mapping, a bijective mapping that preserves the delta Aluche transform for products of operators is a star isomorphism. So again, you obtain linearity. And the result is also true for some other binary products. Okay, so we want to do something in this direction. But the main topic of this talk is truncation. So let me say what the truncation of operators is. This was recently introduced by two Chinese mathematicians. So if we take an operator and we take the orthogonal projection of the closure of the image of the operator, then given two operators A and B, A is a truncation of B if A is equal to this product. Here you have this projection, and this, of course, is the same projection but onto the closure of A star H. Okay, so that's the definition of being a truncation, and they characterize this notion by proving that A is a truncation of B if and only if A star equals AB star B. Okay, so once they have this new notion, they study preservers of truncations. Okay, so first we need to see a few definitions. Well, an operator is a clear projection if it satisfies this. It's an symmetric idempotent. And also a partial isometry is something a bit more general than a projection. It's an operator such that U star is a projection, and this is equivalent to U star U being a projection, and this is also equivalent to this. That we shall see later that this means being a tripotent. So every operator has a polar decomposition, which means that it can be decomposed in the form A equal U times the modulus of the operator, where this U is a partial isometry such that U star is the projection onto the final space of A, and U star U is this other projection onto the initial space of the operator. And then if we look at the Pierce decomposition relative to a partial isometry, which is a decomposition like this one, where the T spaces are given here, and we take the Pierce2 projection, which is the projection from A to the Pierce2 space, then this projection is given exactly by this. So what this means is that if we come back to the definition of truncation, is that an operator A is being a truncation can be reformulated in terms of the Pierce projection, of this Pierce2 projection, but we shall get back to this later. Okay. Well, the problem this Chinese mathematician study is, well, additive maps that preserves truncations. Okay, so what they show is that they are essentially multiples of a surjective result. Okay? They actually study surjective additive maps that preserve truncations in both directions. That means that here you have an if and only instead of just an implication. Later, okay, these are not the same. One of them is the same author, but the other two are Jia and Shi. They take a non-necessarily linear bijective mapping that preserve truncations of products as operators. So what they do is that they study this property, right? So you have A is a truncation of this product, then phi of A is a truncation of the product of phi of B and phi of C. And this is called preserving truncation of products. And when you have an if and only if here, then you call it truncation, preserving truncation of products in both directions. So what they discover, what they prove, is that every bijective mapping between B of H spaces that preserves truncations of products in both directions has this very nice form. Okay? So they also consider some other binary products, so they consider like truncations of geometrical products in this sense, and they also are able to characterize these truncation preservers, these not necessarily linear truncation preservers. Okay? Now we need to give some other definitions that we are going to maybe need later. So it's well known that if we take B of H, the space of bundle linear operators, this is a Von-Neumann algebra, and its pre-dual are the trace class operators, right? So then the state space, the normal state space of B of H is defined as the elements of the pre-dual that are positive and such that phi of 1 equals 1. And the pure states are the extreme points of this normal state space, and they can be somehow identified with rank 1 projections, which are projections onto a one-dimensional subspace. Okay. We are going to denote in this way the set of rank 1 projections in the Hilbert space H. So given two rank 1 projections, the transition probability from P to Q is defined in this way, and it's equal to this number here. And we say that a bijective linear mapping between rank 1, the sets of rank 1 projections, preserves transition probabilities if it has this property. Okay, so Wigner's theorem says that a bijective mapping that preserves transition probabilities can be obtained in this way. Okay, this is a very crucial result. Also, this has certain relation with what we can call ortho-isomorphisms in the lattice of projections. You know that in the lattice, in the set of projections of a Hilbert space, we can define this partial order here and this notion of orthogonality, right? Then, with this partial order and this notion of orthogonality, it's known that every bijective projection that preserves the partial order and orthogonality in both directions is also, well, a symmetry transformation, right? Which is what we had in the previous slide. So when we have a Hilbert space of dimension greater than greater or equal to 3, symmetrical transformations coincide with these ortho-isomorphisms of the lattice of projections. Well, I'm not going to give many details now. Maybe I'm going to pass quickly here. But a notion of orthogonality can be defined for operators in a Hilbert space by these equalities here, and also a partial order that generalizes the partial orders for projections can be defined in the set of partial isometries. Okay, so Molnar generalized the previous result for ortho-isomorphisms in the sets of partial isometries in a Hilbert space, and he obtained also, well, this description here. Okay. Similarly, with some generalization of transition probabilities for partial isometries, he manages to prove this result that can be seen as a generalization of Wigner theorem, right? So you have a bijection between rank 1 partial isometries that preserves this here that we will call later pseudo probabilities. Then it is of the same form that ortho-isomorphisms. Okay, we will see the triple versions of these results later. So let's now go into the non-associative part of the talk, and what we are going to see is non-associative versions of all these non-associative and ternary versions of all the results that we have presented here, or maybe not all of them, but many of them. So first, we have to define what Jordan algebra is, but I think that maybe most of us already know what Jordan algebra is. So it's a commutative algebra with a product that enjoys this property here, and it's unital if there's an element that has this property here, of course. But we need some very special types of Jordan algebras, which are J-star algebras. So we have a Jordan algebra that is endowed with a complete norm that has this property that says that the product is continuous. And we call this a Jordan-Banach algebra, and it is a J-star algebra if it also has an involution and satisfies this other action here, which is the Jordan generalization of the Gelfandheimer action for C-star algebras. So an example of a J-star algebra is a C-star algebra with its Jordan product, right? Some special type of J-star algebras are the JBW star algebras, which are J-star algebras that are also a dual Banach space. Okay? So these are the Jordan counterparts of polynomial algebras. But we are going even farther because we are also going to work with Jordan triples. So a Jordan triple is a complex Jordan triple. In our case, it's a complex linear space with a triple product that is bilinear in the outer variables and conjugate linear in the middle one, and that satisfies this Jordan identity here. And that satisfies also these three additional axioms, some continuity of the product, this action, this axiom here, and also the last axiom is a ternary version of the Gelfandheimer axiom. So examples of J-star triples, of course, every J-star algebra with this triple product here, every J-star algebra with this triple product here, and maybe something that is not a C-star algebra or a J-star algebra. We take the bounded operators between two complex spaces, maybe not the same. Then it becomes a J-star triple with this product. Then, for instance, rectangular matrices are an example of a J-star triple as well, where is this example with H and K being finite dimensional. Now we are going to move towards the definition of truncations in the triple setting, but we need still many definitions. So first, an element in a J-star triple is a triple if the triple product of itself equals itself. Okay. Each tripotent gives rise to a Pierce decomposition, right? Decomposes the space. The J-star triple decomposes as the direct sum of these three subspaces, which are the eigenspaces of the A operator, which was defined previously. And among the Pierce spaces, the Pierce two spaces is important. We shall see why. But let's just mention that we have a projection from the J-star triple into the Pierce two space, which is given by this formula. And of course, if A were to be a G-star algebra, then this would coincide with the formula for the Pierce two projection that we found so many slides ago. Okay. Also, the Pierce two space has an additional structure because it can be endowed with a Jordan product. So it's a J-star algebra, a Jordan product and an involution. Of course, when A is a C-star algebra, tripotents are partial isometries, and the Pierce two projection relative to a partial isometry that we found at the beginning of the talk coincides with this here. Okay. Well, a JBW star triple again is a J-star triple, which is a dual Banach space. Okay, so it's the ternary version of the von Neumann algebras and the JBW star algebras. An important thing is that if you remember the polar decomposition that was given at the beginning of the talk, an element decomposed as a product of a certain partial isometry and the modulus of the element. In a JBW star triple, we don't have a polar decomposition, but there is a special hypothesis associated to every element that plays the role of the partial isometry in the polar decomposition. this tripodent is in principle in the second dual if A is not a JBW star triple, and is in A if A is a JBW star triple, and has the property that is the smallest tripodent satisfying that the element A is positive in the JBW star algebra, which is the Peirce space of the tripodent. Okay, we shall call this tripodent the range tripodent of an element, and when A is a star algebra, it coincides with the partial isometric in the polar decomposition of the element. So now we're going to review truncations of operators. We go back to the original setting, which was B of H. Remember that we saw that the Peirce projection was given by this formula here, right? And also, you know, these two projections were the final initial projections of the range partial isometry. So we can say that given an element A, B, A is a truncation of A is if A is equal to this here, right? We take the range projections of the element A, we take the Peirce projection of the range projection of A and apply it to B, and this has to coincide with the element A. Also, in the original, in the first definition of truncations, we also mentioned that the characterization given by the authors that introduced truncations said that A is a truncation of A if and only if A star equals AB star A. But this, if we consider the definition of the triple product in a star algebra, can be written in terms of the triple product. And also the Peirce projection can be written in terms of the triple product. So we can reformulate everything and say that A is a truncation of B, which now means this here in terms of the Peirce projection, if and only if these two triple products coincide. So now everything is given in terms of the triple product, and this will allow us to define truncations in a J-star triple. First, we need to talk about annihilators in the Jar setting. So given a J-star triple and an element, a fixed element, we define the Q operator by this formula. This is a conjugate linear operator. And for every subset, we can define the outer annihilator of the set by this formula. This should be an A here. And the inner quadratic annihilator of the set can be defined by this other formula. Okay? So now we are going to introduce truncations for general J-star triple. Okay, so we take a J-star triple and two elements in A, and we say that A is a truncation of B if this equality holds, which is exactly the equality that characterizes truncations in the C-star set. Okay, so our first result on truncations is that the same characterization that was possible for C-star algebras also is true for J-star triples, and we have some additional characterization here in terms of elements in the inner annihilator of the element A. So this is our first result on general J-star triples. Recall now that two elements in a J-star triple are said to be orthogonal if this equality here calls for every x in the J-star triple A, but this is also equivalent to A times B equals 0. Okay. And now observe that we can define observe that here in a J-star triple projections doesn't make sense, so we only have tripotents. We can define a partial order in the set of tripotents in a J-star triple. It was the same definition as in the C-star setting. So if we take two tripotents, A is less equal than Q if U minus A is a tripotent which is orthogonal to A. So this is a partial order. And observe now that this notion of orthogonality coincides with orthogonality in a C-star algebra. And this partial order for tripotents coincides with the partial order for partial isometries in a C-star. Okay? So a very nice thing is that actually truncations characterize the partial order. Okay? So if we take two tripotents in a Chebyshev triple, then use less equal than B, if only E is a truncation of B. So very nice thing that truncations have a translation in terms of the partial order. They are the same. So what is the problem we're going to study now? Well, we're going to try to generalize to the triple setting these results about truncations of products of operators. So we are going to study bijective mappings between Chebyshev triples that have this property here. I is a truncation of QBC, so this is the product ACB, right? If only if delta of A is a truncation of Q of delta of B delta C. Okay. Well, this is the general definition of truncation preserver of triple products, but we are going to actually study truncation preservers of triple products in both directions. Okay. Of course, by using the characterization of truncations here, right, this can be reformulated in these terms. Okay. So that's the kind of mapping we are going to study. And well, first we need to think what can we expect of such a mapping. So what would be a mapping that preserves truncations? Of course, a mapping that preserves triple products should preserve truncations, right? Because everything here is given in terms of triple products. So if you preserve triple products, then you preserve truncations. So what we want to know is that if we have a bijection between Chebyshev triples that preserves truncations of triple products in both directions, is it a linear triple isomorphism? Well, we are going to prove this for atomic Chebyshev triples, okay, for some special types of Chebyshev triples. First, we can prove some still general properties of these truncation preservers. In the rest of the talk, delta is always going to be a guy that has this property. Okay. So recall that tripotent in the Chebyshev triple is minimal if its first two spaces equals C times A. So this is, in the case of C-star algebras, what we call the minimal partial isomorphism. Okay. So we have these general properties for truncation preservers in both directions, right? Of triple products in both directions. Then they tend 0 to 0. They preserve outer and inner annihilators. They preserve tripotents in both directions. And moreover, they preserve the partial order of tripotents in both directions. And as a consequence, they preserve order minimal and maximal tripotents. Okay? Let me just remark that a minimal tripotent in this sense that we can call algebraic minimal tripotent is order minimal. So, okay. And actually, in a JBW star triple, this is the same. Okay? Not in general, but being order minimal and algebraic minimal is equivalent in a JBW star triple, which is the setting where we are going to obtain the final results, the main results. So the next property, now I'm going to show our results, but of course I'm not going to give details. I'm going to give just some of the most important results that we get, but I'm not going to get into many details. So we have these properties, and now the that, well, we have our mapping delta. If we take a tripotent delta phase, again a tripotent, and we can show that the Birch2 space of a tripotent A is sent into the bijectively into the Birch2 space of delta of A. Okay, and this has a very nice consequence. We already knew that minimal tripotents were preserved, but we didn't know what happens with the multiples of a minimal tripotent, and now we do know something, because if the Birch2 space of a tripotent is preserved, then if we take a minimal tripotent, what we can see is that delta of C times A is sent into C times delta of A. So this means that we have a bijection F that depends on the minimal tripotent that we are taking, such that delta of the lambda of A is sent to F sub E of lambda of delta of A. Okay. Moreover, we can also show that this mapping has these properties here, right? It sends 0 to 0. It preserves the unit circle, and it is multiplicative. It preserves the conjugation and all these properties here. Okay. Of course, we don't know that this is continuous. We cannot, based on that, we cannot assure that this is going to be lambda or lambda conjugation. Okay, but we have these properties. Well, next, now this was already for general J-star triples. Okay, but now in order to show our main results, we need to move to some very special J-star triples, which are the atomic J-star triples. But first, we need to introduce the Cartan factors, which are the building blocks of atomic J-star triples. Maybe we are not going to stay long in the definition, but well, these are classified in 6 types. Okay, so we have the rectangular Cartan factors. We have the type 2 and 3 Cartan factor, which are some subspaces of B of H. Okay, we have the spin factors, and which are this kind of J-star triples, and we have also the type 4 and 6 Cartan factors, which are also called the exceptional Cartan factors because their product is not special, right? So these are as I said, the building blocks of atomic J-star triples. So what an atomic J-star triple is? It is an atomic J-star triple, actually. All the Cartan factors were already J-star triples, okay? So a J-star triple is atomic if the linear span of its minimal tripotents is weak star in F, okay? It is known that every atomic J-star triple can be decomposed to some L infinite sum of Cartan factors, okay? So that's what I meant when I said that Cartan factors were the building blocks of atomic J-star triples. We shall also need to define the rank of a J-star triple, okay? Because there will be some hypotheses that we refer to the rank. So it's the minimal cardinal R such that the cardinal of an orthogonal set in the J-star triple is minus less or equal to R for every orthogonal set in the J-star. Okay, it's kind of gives you the number of the possible number of orthogonal mutually orthogonal elements in A. And now we also need to, despite the fact that I'm not going to be I'm not going to detail how we use them. These are very important here in this work. Triple transition probabilities. So whenever we have a J without user triple, it's going to have a grid wall, right? Because that's the definition of a J without user triple. So for every minimal triple, there is a pure atom, which is the extreme point of the unit value of the grid wall, that where this minimal such that well, this pure atom P sub A attains its norm at the circle P, and also it happens that the first projection of the tripotent, of the minimal tripotent, can be given in terms of this pure atom, which is called the support of the tripotent, right? And this is a very nice thing because this is saying that well, I'm not going to give details, but that this here on the right hand side is a truncation of X. So that's what we use about triple transition properties. Well, I have not defined triple transition properties, right? So given two minimal partial, two minimal tripletons, the triple transition probability, pseudo probability from A to B is given by this equality, right? So now, if we recall that generalization of Wigner theorem by Molnar, well, what he was studying was preservers of triple transition probabilities, actually, okay, because in B of H they take this form here. Well, we have this is a very important result in our work. This identity principle, which says that whenever we have our delta, a bijection preserving truncations of triple products in both directions, if we already know that delta acts in this form here on every minimal tripotent, so it's linear in the against multiples of minimal partial isometries, and if we know that it coincides with some triple isomorphism on every minimal partial, every minimal tripotent, then actually delta coincides with this triple isomorphism. And the same can be said if instead of linear, we have conjugate linear on multiples of minimal tripotents. So this says that in order to get what we want, that is triple, to show that delta is a real linear triple isomorphism, it is enough to show this, right? That it behaves linearly or conjugate linearly with multiples of minimal tripotents, and that it coincides with a triple isomorphism on minimal tripotents. So first, I'm going to show where this triple isomorphism will come from. It will come from these results by Friedman and Peralta, where they show that when they show that if we have what we can call maybe an orthoisomorphism between the lattices of triplets of two atomic W star triples, right? So we have a bijective mapping between the sets of tripletons of two atomic star triples that preserves partial ordering and orthogonality in both directions. Then, under some additional hypothesis, this one here, you can extend it to a real linear triple isomorphism. So this triple isomorphism here is going to come from an application of these results, okay? And then we will need to show this behavior here, okay? So this is done in many steps. So I'm going to give some results here, skipping all the details. So what we can do first, observe that this result by Friedman and Peralta in particular can be applied to when we have a mapping between the space on N2 or on S2. Okay. So the first thing that we do is we show that when we have a delta, a bijection preserving truncation of triple products in both directions on S2 and N2, then it is linear or conjugative in triple automorphism. Okay, that's the first thing. If we prove, we use our identity principle. We use this result here. We use triple transition probabilities. This is actually kind of too difficult, but yeah, that's a key result in our paper here. The next step is that also skipping many results, many intuitive results, is that we can always reduce somehow to this case here. So what does this mean? What does this mean? Is that if delta is defined between two Cartan factors, whenever we take two multipotents, then we can find a J star subtriple of this guy here, and a JV that contains these two tripotents. So here we can have a JV subtriple N, and here we can have a JV subtriple N subtriple such that delta sends M into N, such that these two tripotents are in M, and such that these are or both or M2 or S2, isomorphic to M2 or S2. And that allows to apply this result later. The next thing that we need to do is to, if we are in an atomic J-star triple, we have to reduce to the case where we have two Cartan factors. So yes, this is actually true if you have our bijection preserving truncations of triple products. It can be shown that every summand here is sent into a unique summand here. So we are in this situation. Okay. And finally, we can show that this mapping that this F sub A, this mapping that we knew that delta of lambda of a minor multipotent was F sub A of lambda times delta of the tripotent. This mapping doesn't really depend on the minor multipotent whenever we're in the same Cartan factor. And actually, this mapping is always the identity or the conjugate. Okay. And yes, this is true for Cartan factors of rank greater or equal to 2. Yes. And there is still one case remaining. Observed here, we didn't need continuity. Unfortunately, there is one case that is not covered by this here. And it's the case of rank 1 Cartan factors. So in the case of rank Cartan factors, we can also have what we want, that delta is a linear or conjugate linear isometry. But in this case, we have to assume continuity. Okay. So for rank 2 Cartan factors, we don't need continuity. For rank 1 Cartan factors, we don't need continuity. And finally, we gather all this together, right? We have, of course, we have to exclude also one-dimensional, the one-dimensional rank 1 Cartan factors, right? Because we have here an example of a bijection preserving the truncation of triple products, which is not additive. Okay. So finally, we gather all this together. We have two atomic JVW star triples. We can separate summands, do everything on about the restriction between two Cartan factors, and we put everything together now in the final main theorem. And actually, we're able to show that whenever we have a bijection preserving truncations of triple products in both directions between two atomic JVW star triples that do not contain one-dimensional summands, and such that the restrictions to the rank 1 summons, only to the rank 1 summons, is continuous, then we have an isometric real triple isomorphism. Something more can be said, because we can separate, of course, summons where delta is linear and delta is conjugate linear, and say that, well, you can split A in two parts where delta acts as a complex linear map and another map where it acts as a conjugate linear map. But in general, we say that delta is an isometric real linear triple isomorphism. That's the main result. Here are some references, some selected references, and that's all. Thank you very much for your attention.
Thank you, Jordi, for the nice presentation and the tempting results on preservers. So can I ask if anyone in the audience would like to make any comments or pose a question to our speaker? You're welcome to pose any question you have in mind.
Sure.
I think all my questions were answered.
Okay, thank you, Michael.
Thank you very much, Jorge.
Thank you.
Well, may I make some connections, some comments, or pose
Of course.
some goals for the future? I think probably the audience, people in the audience are missing the natural question: if what about if we already have linearity and we have some linear mapping preserving truncations? I think this is already solved by some other colleagues and ourselves, but we simply had no time to write it down in a paper. So it will come
Work in progress.
It's a work in progress, but it's the natural question. What about linear maps preserved?
Yes, because actually the first result of truncation preservers was for additive preservers. We jumped to the non-linear case.
Yes, I think we skip it, some of the natural questions, but they are completely independent principles.
Yes.
These results. I simply have a couple of comments concerning the presentation. I don't think that the original definition of truncations is coming by this Zhao and Ji, this Chinese. I think it's a much older notion. It's coming.
Okay.
I think it's already in books on linear algebra, but I'm not sure. I couldn't find. I think it was already in the 70s.
Okay, I was unable to track other reference. Okay.
Yes, I couldn't find who was the first one solving that. Defining that. And there is also a natural comment. I mean, you spoke about transition probabilities and pseudo-transition probabilities in the case of tripotents. So it should be commented that these two notions are in the setting of quantum mechanics. They appear in the connection between Wigner and Ulrom's theorems, and both are very deep results. Well, in quantum mechanics and also in mathematics, in functional analysis. So we expect that some of new applications of these results could be throw some new light into the mathematical models in quantum physics or something like that. But they are related by deep results in quantum physics and mathematics. I mean, you need a whole theory proven equivalence between model preserving partial isometries and order and orthogonality, and also those maps preserving transition probabilities. This is not a stupid thing. I think these are deep.
Yes. I actually skipped the result on preservers of triple transition probabilities, but probably
if you
should be included as well, because I included the case of partial isometric.
yes, if you allow me to insert Songat, I think in the next IWOTA meeting in Canterbury, I will speak about this use of transition probabilities and so on in the case of triples in general. So is there any other comment or question, or excuse me for commenting so long? No one else would like to comment any counterexample that we are happy? Well, what can I say? It's a huge pleasure to see all of you. My personal feeling is that the interest on Jordan theory is growing. Never went to zero, but this is growing. I'm pretty convinced that there is a fantastic Brilliant future for the Jordan theory, not only for geometry, functional analysis, and also for algebra. So keep in touch. Thank you so much to the organizers of this very nice seminar, online seminar. Please count on me to attend to your seminars. I'm very happy to see many familiar faces, and I hope to meet you in person sooner or later. So I think that's all for today.
Thank you everyone.
Thank you, Jordi.
Thank you, Antonio.
Thank you, Antonio, for the chairman. It was a pleasure to see you.
Thank you.
And so we see each other in Braga, I guess.